Okay, let's go with that. All right. Yeah, sorry for the delay. So, uh, the big question that underlies this talk is, does there exist a density-sensitive bifiltration of metric data that is at the same time computable and robust to outliers? And so we don't have an answer to this question yet, but we do know a fair bit about this question and about surrounding things. And so that's what I want to talk about today. I'm going to be discussing a number of references, but the main references are first a paper that I wrote with Andrew Bloomberg called The Stability of Two-Parameter Persistent Homology. This treats the robustness question. And then I'll also be talking about joint work with a PhD student at UAlbany named Ken McCabe on subdivision RIPS bifiltrations. Ken has been a PhD student at Albany for only about a year, but he's already kind of really off to the races in research and has made some good progress. And I'm excited to tell you a little bit about what he's been doing and what we've been doing together. So TDA considers several filtrations built from point cloud or metric data that you know, the offset or union of balls filtration, via torus RIPS, the alpha filtration, also called the Delaunay filtration. And for each, we have a stability result. So for example, in the case of RIPS complexes, the result is that the Gromov-Hausdorff distance between finite metric spaces P and Q is greater than or equal to the bottleneck distance between the homology modules of the RIPS filtrations of P and Q. So in this paper with Andrew Bloomberg that I mentioned, we give closely analogous stability results for density-sensitive bifiltrations. Okay, and the bifiltrations that we consider in this work all require no extra parameter choices, and results guarantee robustness of these constructions to outliers, sometimes in a strong sense, sometimes in a weak sense, depending on the specific construction. But together, these results reveal a tension between robustness and computability for the two-parameter setting that I'm very interested in understanding better, hence the title of this talk. So let me start by reminding you what a bifiltration is and specifying what kind of bifiltrations we'll look at here. So for totally ordered sets S and T, an S by T bifiltration is a functor from the product partial order of S and T into top, whose structure maps are inclusions. In this talk, we'll take S and T to both be non-negative real numbers, and we'll let S have the opposite of its usual total order. So what that means is that our parameter space for our bifiltrations is the upper right quadrant in the plane, and our arrows, which index inclusions, go to the left and up, like shown here. So we also need a notion of topological equivalence of bifiltrations, and fortunately there's a standard one in algebraic topology called weak equivalence. So given a poset and poset P and functors F and G from P to top, we say that a natural transformation gamma from F to G is an object-wise homotopy equivalence if each of its components is a homotopy equivalence. Now, this doesn't give you an equivalence relation, but it generates one. So we say F and G are weakly equivalent, which we denote like this, if there exists a zigzag of object-wise homotopy equivalences connecting F and G. And in fact, it suffices to take that zigzag to have just one intermediate functor and to look like this. And if F is weakly equivalent to G, then we say F is a model for G. So the best known example of weak equivalence in topological data analysis is that the offset and check filtrations of a point cloud in Rn are weakly equivalent. And you can see that if you dig into the usual, say, Hatcher proof of the Nerve theorem. Now, weakly equivalent functors have isomorphic homology, and in practice, we're usually working with homology, but when stating results, it's sometimes nice to work directly on the level of filtrations using this language. So I'm going to discuss two density-sensitive RIPS bifiltrations. And I should say that in the interest of time, my emphasis in this talk is going to be primarily on the RIPS setting, although interesting things can be said in other settings as well. So I'm going to talk about Sheehy's subdivision RIPS bifiltrations and also a construction called the degree RIPS bifiltration. So first, let's talk about subdivision RIPS. And my notation will be that C and R denote the check and RIPS filtrations respectively. And I'll let T be a simplicial complex, T plus its barycentric subdivision. And so the first thing we need to say is that vertices of the barycentric subdivision of T correspond to simplices of T and therefore have a dimension. For example, consider this vertex here in the barycentric subdivision of this simplicial complex T. Right, this guy corresponds to this one simplex in T, so we think of that as having dimension 1. This vertex in the barycentric subdivision corresponds to this 2 simplex in T, and we can think of that as having dimension 2. So filtering this barycentric subdivision by decreasing vertex dimension yields a filtration that I'll denote ST like this. So in the case of T from the previous slide, the filtration looks like this. All right. And now this vertex here has dimension 2, we said, so you might wonder why I index this complex as 3. Well, I shift my indices by 1 for reasons that I won't get into here, but don't worry about that. So this is the filtration associated to the barycentric subdivision. And now if we have a simplicial filtration, then we can apply this construction at each index in the filtration. We get a 1-parameter family of filtrations, and that assembles into a bifiltration, and we call this the subdivision bifiltration of our filtration. In the case that our filtration is the Vietoris-Rips filtration of a metric space, and we call this construction the subdivision Rips bifiltration of X. And similarly, we talk about the subdivision check bifiltration. Okay, and so here's an example of this. I've got 4 points here in the plane, and I look at their Vietoris-Rips filtration. I've just looked at the first 3 complexes in the filtration, and I take the barycentric subdivision of each. So that's what you see on the right column here, and then filtering this by dimension, as I discussed, gives you a bifiltration that looks like that. Okay, so that's the construction. Now, so I think this is an elegant construction, but it's important to remark that both the subdivision check and subdivision Rips bifiltrations have exponentially many vertices in the size of X. And this raises the question of whether there's a bifiltration weakly equivalent to these or approximately weakly equivalent that has smaller size. And at least for the case of points X in Rn, in the case of subdivision check, we do have an answer. So turns out that the rhomboid bifiltration of Edelsbrunner and Osang that they defined a few years ago, this is a polyhedral bifiltration in Rn plus 1, and it's weakly equivalent to the subdivision check bifiltration. Okay, and then this guy, the rhomboid bifiltration, has O to the size of X raised to the n plus 1 number of cells. And the way that this is shown, I should mention, is by showing that this rhomboid bifiltration is weakly equivalent to a different filtration called the multicover bifiltration. And then it's a result of, essentially by Don Sheehy, that the multicover bifiltration is weakly equivalent to the subdivision check bifiltration. Okay, so this is an illustration of the rhomboid bifiltration. It's a beautiful construction, and I'd like to define it for you, but I won't right now because we don't have time for that. So I'm going to move on to my other discussion, or my other definition of a Rips type bifiltration. This is the degree bifiltration, and the idea here is that any simplicial complex T is naturally filtered by vertex degree. We'll consider decreasing vertex degree. Okay, I mean, any simplicial complex is naturally filtered by any function on its vertices, in fact. So I'll choose vertex degree and take it to be decreasing. So now, just like before for subdivision bifiltrations, I'm going to apply this filtration index-wise to a filtration F, and that yields a bifiltration DF. And then in the case that X is a finite metric space, we call D of the Rips filtration, the degree Rips bifiltration, and that's illustrated here for this point cloud here in R2, just for a few values of the degree in the radius. Okay, so that's my other construction. 2, I think, very natural, simple, elegant extensions of the Rips filtration to the parameter setting, to the 2-parameter setting, and both of them are density sensitive somehow. So, for example, for degree Rips, we can think of the degree as a measure of density. So now to state stability or robustness results, we need metrics on the objects that we work with, and fortunately, we have natural 2-parameter analogs of the usual metrics that we work with in the 1-parameter setting. So let me mention these now. So first, there's a distance between probability measures on a common metric space called the Prohorov distance, which dates back to the 50s. It's very classical. And it's given as follows. So for probability measures mu and eta, this is the supremum over all measurable sets A of the infimal delta such that mu of A is less than or equal to eta of the thickening of A by delta plus delta. And symmetrically, eta of A is less than or equal to mu of the thickening of A by delta plus delta, where the thickening of the set is defined in the way that you would expect, or a way you would expect. Okay, and in TDA, and this distance has been used in places in TDA, but perhaps the P-Wasserstein distance is more popular. This distance, the Prohorov distance, is a lower bound for the square root of the P-Wasserstein distance. So any stability result that I state using Prohorov yields a stability result for Wasserstein via this proposition here. Okay, so just like we extend the Hausdorff distance to a Gromov-Hausdorff distance, which concerns data not embedded in a common space, we can do a similar thing for Prohorov distance. So we can extend to probability measures mu and eta on possibly different metric spaces x and y. And to do this, we embed x and y isometrically into a common metric space Z, and then we push forward the measures on x and y, take the Prohorov distance, and now we consider all such possible isometric embeddings, take the infimal Prohorov distance. That's Gromov-Prohorov. Okay, and so this distance has a nice robustness property with respect to outliers, which says that if y is a finite metric space and x is a non-empty subset of y, then the Gromov-Prohorov distance between the uniform measures of x and y is less than or equal to the number of points that in y that are not in x divided by the number of points in x. So if x has very many points and I add just a few points in to x to get y, then their Gromov-Prohorov distance is going to be close. Okay, that's robustness with respect to outliers. And now I want to observe that in my setting, I have interleavings, right? So remember, I'm working over the poset 0 infinity op cross 0 infinity. And all I want to say about this for now, I mean, this slide has a lot of notation on it, but the main point is that you can define interleavings here the way that you would expect, and the shifts go to the left by delta and up by delta. And then we have an interleaving distance associated with this. And now I have enough language to state our main stability result, which says that for all finite non-empty metric spaces x and y, the Gromov-Prohorov distance between the uniform measures of x and y is greater than or equal to the interleaving distance between the homology modules of the subdivision RIPS bifiltrations of x and y. And if I had a bit more language, I could state this directly on the filtration level without talking about homology, but I won't bother with that. And okay, so I'm just stating a result for RIPS filtrations, but we also have an analog for the multi-cover subdivision check or rhomboid bifiltrations. And once you have a result for one of these, you have it for all of them because of homotopy invariance, essentially. Okay, one technical remark is that to make this work, you need to normalize the indices of subdivision RIPS in an appropriate way, but I won't go into that. About the proof of this, it closely follows the proof of ordinary RIP stability, the original proof due to Chazal and company, where they use the nerve theorem, and here the key novel tool that we need, or well, it's not, we didn't come up with it, but it's sort of novel to the proof strategy, at least. This is Sheehy's multi-cover nerve theorem, which I think I mentioned before in passing. All right, so what this is a close analog of ordinary RIP stability in the one parameter setting, but now we're in the two parameter setting, and this result is density sensitive and somehow outlier robust somehow. Now, we of course want to ask whether there's an analog for degree RIPS, and there is. This concerns generalized interleavings, however. And so here, the difference is that whereas if you go back to this slide from before, our shifts in our interleavings were to the left by delta and up by delta. Now the shifts are going to be affine maps that depend on the index. So we're going to shift to the left by delta and then up by 3r plus delta, where r is the radius parameter for us. So in my diagram, this is the degree parameter and this is the radius parameter. And so we would want this 3 to not be here. Having this 3 involved in the interleaving makes this a much weaker form of robustness / stability, but the result is tight. A simple example shows that you can't improve that result of 3 and still get an analogous bound in terms of Gromov-Prohorov distance. And what you can do, however, which Louis Skokola and Alex Rolla did, is give a Lipschitz stability result for degree RIPS if you use a stronger distance. So they use a distance called Gromov-Hausdorff-Prohorov, which is like the Gromov-Prohorov distance that I defined before, but when you embed the points into the common metric space, you also require that they're Hausdorff close. And that's a big additional constraint. So that gives you a distance that's density sensitive, but not robust to outliers. Okay. So anyway, that's another part of the story here. So that is the robustness side of things. And let me turn now to a discussion of computation, and we'll also talk about sizes of things because that's related to computation, of course. So degree RIPS, our less robust construction, is also our most computable one. The M skeleton of degree RIPS has size say degree RIPS of a metric space X has size O to the number of points in X raised to the M plus 2. But if we snap our bifiltration to a grid of constant size, and this drops to O to the size of X raised to the M plus 1, which agrees asymptotically with the size of the M skeleton of the ordinary RIPS filtration. So these guys aren't too huge. And in fact, one can compute these. This has been implemented in the software Rivet by Roy Zhao several years ago, in fact. And one can compute one-dimensional skeleta for these guys for thousands of points. And with more implementation tricks, you probably can go significantly beyond that. And so, right, so these are computations that we have done and do, and you can apply them to practical data sets. Like this is something that's practical, at least for studying cluster structure, right? One-dimensional skeleta give you H0, which sees cluster structure. And as you go up in dimension, things get more expensive. So, okay, I mentioned the rhomboid bifiltration, this polyhedral model of subdivision check. This also can be computed in polynomial time. Edelsbrunner and Osang have an algorithm for this. And Osang even has an implementation for R2 and R3. And so you can do these kinds of computations, but these rhomboid bifiltrations are quite huge in practice. So what you can do to make things more practical is just compute this guy up to some value of that dimension, K, in their software. Their algorithm allows for that. Okay, and I don't want to say too much more about those computations, but I will mention that in this direction, Boucher and company recently gave a linear size approximation of the multi-cover bifiltration up to some fixed value of K, which is a nice result. Although the size of their construction depends exponentially on K, so that's a limitation. All right, now the last thing that I want to talk about is computation of subdivision RIPS bifiltrations, and this is joint work with Ken McCabe that I mentioned at the very beginning, although this header here is a bit of a lie. I'm not going to say so much about computation. What I want to talk about primarily is the size of models of subdivision RIPS, which of course is closely related to computation. So here's a theorem in 4 parts that summarizes our main findings about this. So first is a negative result. Ken discovered that there doesn't exist a polynomial size cellular model of subdivision RIPS in general. And that's even true for X in R2. That's even true for X lying on the unit circle. Okay. So not only is subdivision RIPS exponentially sized, but any model of it is in that level of generality. But there's good news. So number 2 is that there does exist a polynomially sized cellular model of subdivision RIPS for X in any Euclidean space with the L1 metric. Okay. And for any LP metric in fixed epsilon greater than 0, there exists a polynomially sized epsilon approximation to subdivision RIPS. Okay, where epsilon approximation is approximation in the interleaving distance. And in these results 2 and 3 here, polynomially sized, actually for 1 through 3, polynomially sized means something specific. I mean that the fixed dimensional skeleta have polynomial size. And then finally, for all x, there exists a 2 approximation to the subdivision RIPS bifiltration that not only is polynomially sized, but also isn't too huge. So specifically, this has quadratically many vertices with respect to the size of x. And the one caveat here is that this 2 approximation that I'm mentioning is not a genuine bifiltration, it's a functor. Okay, and I mean, one could convert it to a bifiltration, but I'm not sure whether this size bound holds when you convert to a bifiltration. Okay, so what else to say? Now, recently we've been thinking about how to actually compute these guys, and we think that these models can be computed in polynomial time. They're not just polynomial sized, you can compute them in polynomial time, but with the possible exception of number 4, I don't claim that these things are anywhere near the realm of practicality, because these bounds that I'm mentioning here in 2 and 3 hide constants which depend badly on both the embedding dimension of the data and the approximation error. Okay, so at least, I mean, this work is definitely practically motivated, but for the moment, these results are, you know, we'll call it like a first theoretical inquiry into these kinds of questions. So then one big question for us is, does this result 3, this approximation result, extend beyond data living in Rn with LP metrics to metric spaces of bounding doubling dimension? And that's something that interests us a lot, and we've been thinking about it, but we don't have an answer yet. And then secondly, I want to mention regarding this 2 approximation, that so until recently, the best we knew of this was that we have a 3 approximation to subdivision RIPS, because actually degree RIPS is easily seen to be a 3 approximation of subdivision RIPS. But it turns out that there's actually a 2 approximation. And one thing that's interesting to me that I don't know is whether this constant 2 can be lowered even further. I haven't really thought about it, but maybe it can, who knows. So, and let me emphasize that this is for all x, right? Okay, so then I'm about out of time, but I thought I'd close by saying a little bit about how we get at these things. And there's kind of a master theorem that implies these results, which says that for x, a given family of finite metric spaces, there exists a polynomially sized model of subdivision RIPS bifiltration of x, if and only if each RIPS complex, each ordinary RIPS complex has polynomially many maximal simplices. So the moral is that the number of maximal simplices really controls how bad things get. And so to construct this model that's mentioned here, for each R, you can cover each RIPS you can cover the RIPS complex by its maximal simplices. And that turns out to induce a functorial cover of the subdivision RIPS bifiltration. Then you can apply a version of the persistent nerve theorem, and the result is a functor. It's not a bifiltration, but it can be converted to one. So I've illustrated that construction here on this slide. Like the top is the cover of the example that we saw before, and the bottom is this bifiltered nerve. So I think I'll stop there, but I'll be happy to take questions. Thank you.
So, any questions?
This epsilon approximation in the slide spec, is that multiplicative in the living distance or additive?
I'm sorry, it is very hard to hear. I could hear maybe 20% of that.
I can try again. So this epsilon approximation that you're talking about, is that multiplicative in the living distance or additive?
Oh yeah, now I understood. Yeah, it's a multiplicative. We're talking about multiplicative interleavings, and that just requires interleavings with respect to the radius parameter and not that dimension parameter.
Any other questions? Okay, so if there are no other questions, let's thank Michael again for a very nice talk.
There is one question.
Oh, there's one question from Alex. So the question
Is there a canonical way to find a polynomial model for a persistent space?
Yeah, I mean that's a great question. I don't have a good answer, but I will say that this construction that I'm describing here on the last slide is a bit more general than I've said. So this at least applies to other subdivision bifiltrations besides subdivision rips, where instead of, yeah, I mean, you can just, basically the same thing works for other subdivision bifiltrations. But beyond that, I don't have any insight into something more general, more systematic that you could do.
Any other questions? Not coming. No.
Yeah.
All right, so let's thank Michael again.
Thank you.